Imagine stepping into a time machine, one that could traverse not only billions of years but also countless light years of space, all in search of life in the universe. Where would you find most of it, and what would it look like? The answer, or at least scientists' best guess, might surprise you. You might think most life out there would be like what we see on Earth today: grasses, trees and frolicking animals all orbiting yellow stars on watery worlds under blue, oxygen-rich skies. But you would be wrong. Astronomers conducting a galactic census of planets in the Milky Way now suspect most of the universe's habitable real estate exists on worlds orbiting red dwarf stars, which are smaller but far more numerous than stars like our Sun. In part because of their immense numbers, such stars are in some respects easier for astronomers to study. Consider, for instance, the red dwarf star called TRAPPIST-1, just under 40 light-years away. In 2017, astronomers discovered it is orbited by at least 7 temperate Earth-size planets. A plethora of new observatories, chief among them NASA's multi-billion-dollar James Webb Space Telescope, slated to launch in 2019, could soon begin studying the planets of TRAPPIST-1 and other nearby red dwarf planets for signs of habitability and life. In the meantime, no one really knows, of course, what you would see if you visited one of these strange worlds in your planet-hopping time machine, but if they are at all like Earth, chances are you would find a planet dominated by microbes rather than charismatic megafauna. A new study published in the January 24 edition of Science Advances explores what this curious fact might mean for alien-hunting astronomers. Co-authored by David Catling, an atmospheric chemist at the University of Washington in Seattle, the study peers deep into our planet's history to devise a novel recipe for finding single-celled life on faraway worlds in the not-too-distant future. Right here on Earth, most life is microbial, and a careful reading of the planet's fossil and geochemical record reveals it always has been. Organisms like plants and animals, as well as the oxygen the plants produce and the animals breathe, are relative newcomers, having only arisen in the past 500 million years or so. Of the remaining 4 billion years of Earth's history, our planet seems to have spent its first 2 billion as a slime world ruled by methane-belching microbes for which oxygen was not a life-giving gas, but a deadly poison. The emergence of photosynthetic cyanobacteria, named for their verdant hue, which comes from chlorophyll, defined the next 2 billion years, and banished the methanogen microbes to dark places where oxygen could not go, subterranean caverns, deep muds, and other smothered environments where they still exist to this day. The cyanobacteria gradually greened our planet, slowly filling the atmosphere with oxygen and setting the stage for today's familiar world. Touching your time machine down on Earth at a random point in the planet's history, roughly 9 times out of 10 you would only find single-celled life or algae and would risk suffocation in the oxygen-starved open air. This creates a quandary for scientists hoping to use the Webb telescope, rather than a time machine, to seek out other life-bearing worlds. Molecules in a planet's atmosphere can absorb passing starlight, imprinting barcode-like signatures on the light that astronomers can then detect. Plentiful oxygen in a planet's atmosphere is one of the most obvious barcodes to look for in a planet's atmosphere across the light years, because it is one of the hardest things to make sans biology. In the parlance of astrobiologists, the highly reactive gas is a potent biosignature, because in large concentrations it tends to be out of equilibrium with its surroundings. That is, oxygen tends to fall out of the air as rust and other mineral oxides rather than linger as a gas, so when it exists in abundance, something, photosynthetic life, in Earth's case, must be constantly replenishing it. But with our planet as their guide, astrobiologists are forced to acknowledge that oxygen may be the least likely thing they will ever see. Genetic evidence suggests the complex oxygen-producing photosynthetic pathway pioneered by cyanobacteria is an extraordinary evolutionary innovation that only appeared once throughout the entire multi-billion-year history of Earth's biosphere. One might expect, then, that in any living, Earth-like, world scientists will ever gaze upon through telescopes is likely to be anoxic, or lacking in oxygen. What other biosignatures should they seek instead? Right now, the best way to find an answer is to hop back into the time machine. Not a real one, of course, but rather a virtual Voyager, a computer model that plumbs the otherwise inaccessible depths of Earth's anoxic past or an alien planet's present, exploring the possible chemistry of gases in the atmosphere and ocean that could have occurred there. Use data from old rocks and other models to dial in your best guess for the environmental conditions of, for instance, the Earth circa 3 billion years ago. Let the computer crunch the numbers, and see if any obvious imbalances, potential biosignatures, pop out. This is exactly what Catling did, working with his doctoral student Joshua Chrysansontartan and Stephanie Olson, a PhD candidate at the University of California, Riverside. Their time machine is essentially just a numerical approximation of an immense volume of air trapped in a large, transparent box with the open ocean at the box's base. The computer simply calculates how the constituent gases in the box should react and mix with each other over time. Eventually, the interacting gases use all the free energy available in the box and reach equilibrium, a point where no further reactions can occur without more energy from outside, a bit like soda water that has lost its fizz. Comparing the cocktail of exhausted gases with the livelier mixture originally trapped in the box reveals precisely where and how the world's atmosphere was initially out of equilibrium. From first principles, this approach can replicate the most obvious example of atmospheric disequilibrium today on our planet, the presence of oxygen and traces of methane, the latter being the gentle exhalations of the once mighty methanogen biosphere. Simple chemistry shows these gases should not coexist for long, and yet on Earth they, offering a clear sign for any watchful alien astronomers that something lives and breathes on this particular pale blue dot. But for the ancient, anoxic Earth, the modeling shows something different. Our research provides the answer to the question of how to find anoxic life on an Earth-like planet, Catling says. Most life elsewhere is probably simple, like microbes, and most planets have probably not advanced to a stage of an oxygenated atmosphere. The combination of relatively abundant carbon dioxide and methane absent carbon monoxide is a biosignature of such a world. Chrysansontartan explains in more detail, having methane and carbon dioxide together is unusual, because carbon dioxide is carbon's most oxidized state, and methane composed of a carbon atom linked to 4 hydrogen atoms rather than any oxygen at all is its least, he says. Producing those two extremes of oxidation in an atmosphere at once is challenging to do without life. A rocky, ocean-bearing planet with more than 0.1% methane in its atmosphere should be considered a potentially inhabited planet, the researchers say. And if the atmospheric methane reaches levels of 1% or more, in that case, potentially, doesn't cut it, such a world would likely be home to alien life. Jim Casting, an atmospheric chemist at the Pennsylvania State University unaffiliated with the study, says its results are on the right track, even though the idea that methane might be a biosignature in an anoxic atmosphere is not exactly new. What is new, Catling and his co-authors say, is their robust treatment of how a methane-based biosignature would manifest itself, and how it could be discerned from non-living sources. According to their models, methane in the atmosphere of an anoxic Earth-like planet would typically react with the carbon dioxide that still filled the air, mingling further with another ubiquitous gas, nitrogen, as well as water vapor to ultimately rain out as heavier compounds. Further calculations by Catling and his team conclude that no abiotic methane sources on a rocky planet could produce enough of the gas to counteract this process, whether it is volcanic outgassing from a planet's interior, chemical reactions in hydrothermal vents, even asteroid impacts. Only a thriving planetary population of methane-belching bacteria could account for the gas. And, most crucially, even if abiotic sources could come up with enough methane, they would almost inevitably produce a great deal of carbon monoxide as well, a gas poisonous to animals but positively delicious to many microbes. Thus, methane and carbon dioxide together, unaccompanied by carbon monoxide, on a rocky, ocean-bearing world would best be interpreted as an airtight sign of anoxic life. This is good news for astronomers. The Webb telescope, it turns out, will be hard-pressed to directly discern oxygen in any potentially habitable planet it surveys during its mission. Just as your eyes can see visible light but not radio waves or X-rays, Webb's vision is tuned for the infrared, a portion of the spectrum ideal for studying ancient stars and galaxies, but where oxygen's barcode-like absorption lines are rather slight and sparse. Consequently, some researchers have feared the search for life would have to wait for other, more capable telescopes many years or decades in the future. But although Webb cannot easily see oxygen, its infrared eyes could excel at glimpsing signs of anoxic life. According to Nicole Lewis, Webb's project scientist at the Space Telescope Science Institute in Baltimore, the telescope could perform the simultaneous detection of methane, carbon dioxide, and carbon monoxide in the atmospheres of some planets around red dwarf stars. And not just big, bloated gassy planets where we wouldn't expect life to exist anyway. Webb can achieve the required precision to detect the molecules in the atmospheres of planets like those in the TRAPPIST-1 system. Lewis says. Even so, Lewis and others note that Webb could still struggle to fulfill the most crucial part of Catling's criterion, determining the relative abundances of each gas to pin down whether methane on some distant planet is due to an erupting volcano or burping microbes. Consequently, Catling isn't holding his breath for Webb to find an anoxic biosphere on some red dwarf world. Webb probably has to get lucky to find life, but you never know, so this is potentially exciting for astrobiology, he says. We want to make more people aware that there's more to looking for life than looking for oxygen.